everyone and welcome to Chapter 3 video number 4 in the 3-phase induction machine course. If you remember, in video number 1 we covered the power flow diagram. In video number 2 we covered torque speed characteristics. In video number 3 we had 2 examples to cover power and torque calculation, while in this video we are going to wrap up this chapter by a comprehensive example on power and torque calculation. Example: a 415 line value, 20 horsepower, 50 Hz, 4-pole, star-connected, 3-phase squirrel cage induction motor has the following parameters referred to the stator side at standstill per phase. And we know what the meaning of standstill, that we can have the rotor resistance physical value. So we have the value for R stator, R rotor, X stator, X rotor, and XM. If you notice as well that I didn't add for X stator, X rotor, XMJ, but when you are going to solve the problem, you need to add the imaginary operator J. So the total rotational loss is 1.1 kilowatt and is assumed to be constant, and they are lumped with the rotational losses. So we are going to add it to the end of the power flow diagram. So for a specific slip, 2.5% at rated voltage and frequency, but I didn't mention at rated power. Said that at rated voltage and frequency. So we apply 415 volt line value and the supply frequency is 50 Hz. But we didn't mention that the power is 20 horsepower output. So we need to calculate air gap power, developed power, rotor copper loss, motor developed torque at the above operating point, motor efficiency at the above operating point, net torque, slip for maximum torque and speed at which will occur, maximum torque, and starting torque. Also, I'm going to simulate the results at the end of this example to see how the simulation is going to confirm the analytical values. So we can start the solution by listing the given. So we have a squirrel cage induction motor, definitely 3-phase. We have number of poles 4, star connection, and the line voltage is 415 volt. And we are going to solve the problem per phase. So we are going to have the phase value 415 over root 3. And I'm going to assume that the phase voltage is angle 0 degrees. Supply frequency is 50 Hz, and we have a specific slip 2.5% or 0.025. The motor parameters are R stator, R rotor, X stator, X rotor, and if you notice here I start adding the J to X and X. Also XM is J28, R core is infinity. So we can use the first approximate equivalent circuit. Core rotational losses equals 1.1 kilowatts. We're going to use it when we're going to calculate the output power. But before we leave the given, I need to highlight important notes. I mentioned that one when I'm listing the problem or introducing the problem. The machine is operating at a specific slip. This is not the rated power output. So maybe the rated output power, 20 horsepower at another slip. So the 20 horsepower is not the power we are going to use in this case. To have or to use the 20 horsepower, we need to mention that the machine is operating at the rated output power. That one is totally different if the machine is operating at rated voltage and frequency, but we have different loading conditions, different mechanical load for different slip, so this means that the output power is not 20 horsepower. And we are going to prove that one later at the end of the problem. As I mentioned, that we are going to use the first approximate equivalent circuit, and to solve this problem and find all the power, or to calculate the power and torque, we need to calculate the rotor current, stator current, and we have at the same time synchronous speed and rotor speed. If you remember, from Chapter 2, video number 4, example 2, we have the same parameters, same voltage, same frequency. So we are going to use these values as a starting point for this problem, rather than we are going to repeat another video. So we have synchronous speed is 1500 RPM, omega s is 157.1 radian per second. We have rotor speed 1462.5 RPM, and omega r is 153.2 radian per second. We have rotor current 17.62 and angle minus 8.5 degrees, and stator current is 20.7 and angle minus 32.6 degrees. So we are going to start from this point here. If we like to calculate power input, we have supply voltage, we have stator current and an angle between them. And if you like to calculate for the rotor side, we have the rotor current. So let's start for part A. To calculate the air gap power, we can say that B gap equals 3I rotor square R rotor over S. From where you got this formula, so you need to return back to the previous videos, video number 1, to see the power flow diagram in this chapter. So that one equals 317.62 square multiplied by R rotor over S. So that one gives you 11.92 kilowatt. So that one is the air gap power. So we can calculate the developed power as well. The developed power equals 3I rotor square R rotor 1 minus S over S. Or you can use B gap 1 minus S. So that one will be 11.62 kilowatt. So the rotor copper loss, you can calculate it using SB gap or B gap minus B developed, or 3I rotor square R rotor, any one of them. So that one will be 3I rotor square R rotor or SB gap equals 300 watt. So the developed torque, we have omega S, we have omega R, we have B gap, we have B developed. So we can use any equation of them. So torque developed equals B developed over omega R or B gap over omega S will give you the same value, 75.88 Newton meter. Now we can calculate the net torque. So to calculate the net torque, we need to calculate the net power. So the net power equals B developed minus rotational loss. P developed we calculated from the previous slide, and rotational loss is given, and that one contains both mechanical loss and core loss together. They are lumped together. So 11.62 kilowatt minus 1.1 kilowatt gives you 10.52 kilowatt output power, net power, shaft power. So the net torque or shaft torque or useful torque equals B net over omega R, 10.52 kilowatt over 153.2 gives you 68.7 Newton meter. But I need to focus on this number or this value. So 10.52 kilowatt, how many horsepower we have? So we know that 1 horsepower equals 746 watt. So that one is equivalent to 14.1 horsepower. And the motor is rated at 20 horsepower. So 20 horsepower equivalent to 14.92 kilowatt. 14.92 kilowatt. So look for this value and this value. So definitely the motor is not operating at the rated power. So now the motor is operating at 14 horsepower while the motor rated power is 20 horsepower. So we can load the motor more up to 20 horsepower. But at this slip or specific value of the slip, 2.5%, we are under the rating from 20 horsepower to 14 horsepower. So how to calculate the motor efficiency at this slip? So the motor efficiency is net power over input power, and the input power is 3V phase I phase cosine phi. Or you can use root 3V line I line cosine phi. But remember that cosine phi is the same cosine phi here, which is the angle between V phase and I phase. So input power is 12.54 kilowatt, and the efficiency in this case will be P net over P input, 83.9%. Now it's time to calculate different torque points. So we are going to start by the maximum torque. To calculate the maximum torque, we need to calculate the slip for maximum torque. So the slip for maximum torque, S maximum equals R rotor over root R stator square plus X stator plus X rotor, or we can say X equivalent square. So that one gives you 0.1542 or 15.42%. So once we calculated that one, we can calculate the speed at which maximum torque will occur. So that one is NS1 minus S maximum, and that one at speed 1269 RPM. So we know now S maximum, so we can calculate the torque, maximum torque. We can use the formula directly here, or you can calculate I at S maximum, and then you are going to calculate B gap at S maximum, and you are going to divide that one by omega S, give you the same value. So here I'm substituting the formula 3V phase square over 2 omega S, big bracket R stator plus root R stator square plus X equivalent square. That one gives you maximum torque 200 Newton meter. So what about the starting torque? So S should equals 1. So we are going to substitute the same equation for the voltage, but we are going to put S equals 1, and that one gives us starting torque 71.28 Newton meter. Also, you can calculate that one by at S equal 1. So you are going to calculate I starting, and once you have I starting, you are going to calculate B gap at starting. and then you are going to calculate torque equals B gap over omega S. So that one gives you the same value. As a confirmation for the analytical results, I simulated this problem using MATLAB Simulink, but we didn't know how to do that one. So in chapter number 5, we're going to introduce a simulation using MATLAB Simulink and the M code or MATLAB code. So let's look here for the simulation results. We have the speed 1460 RPM, output power is 11.6 kilowatt, and the motor torque is roughly 75.88. Stator current is 20.5 with angle minus 30 degrees, and the input power is 12.72 kilowatt, and the efficiency is 82.54%. Compare that one with the analytical results. We are almost so close, so they are close values. So the torque here is identical to the torque there, and almost the efficiency is just 1% difference. So let's look for that one using M code. So using M code, we built this problem in the MATLAB code, and then we simulated the torque speed characteristics. We found that starting torque is 71.3 Newton meter, and the maximum torque occurs at the same speed we calculated, 1269 RPM, with maximum value 200 Newton meter. And if we look for the stable region, so we are going to have at slip 2.5%, the speed is identical to what we calculated, 1462, and the torque in this case will be 76.9 Newton meter. Regarding the current, so the current here, we have starting current equals 115.9 ampere, and the rotor current is 108.1 ampere. But looking for the stable region, we have the current at the maximum point is 71.3 ampere or 0.03 ampere. That one is the rotor current, and the current at slip 2.5%, exactly as we calculated for the stator, which is the blue line, and the rotor for the red line, that one at speed 1462 RPM. So in chapter number 5, we're going to see how to plot these curves. That one will be 2 chapters ahead. So let's recap this chapter. In this chapter, we started looking for the power flow diagram. So we found the relation between air gap power, rotor copper loss, and developed power. So then we can calculate the torque or motor torque, developed torque, and shaft torque. So the developed torque equals B gap over omega S or B developed over omega R. To calculate the net torque, we need to calculate the net power, where the net power equals B developed minus rotational loss. So then we start looking for the torque speed characteristics and different points at torque speed characteristics, something like maximum torque. And to calculate the maximum torque, you need to know what the speed this maximum torque occurs. So we need to calculate the slip for maximum torque. S maximum equals R rotor over root R stator square plus X equivalent square. Then you can find the current at S maximum, then the air gap power at S maximum, then you can calculate the torque maximum or directly use this formula T maximum equals. Also, you can calculate the starting torque when S equals 1. You are going to follow the same procedure or use this formula. In some cases, we can neglect the stator resistance. So T maximum equals 3V phase square over 2 omega S X equivalent. From this one, we can find the relation between any developed torque and maximum torque, which equals 2SS maximum over S square plus S maximum square. We can repeat the same formula, find the relation between starting torque and maximum torque. Before we leave this point, I need to highlight that maximum torque does not depend on the rotor resistance, while S maximum in this case, which is R rotor over X equivalent, depends on the rotor resistance, where the position of the rotor or the maximum torque depends on the rotor resistance, while the value does not depend on the rotor resistance. What will I watch in the next chapter? In the next chapter, we are going to cover motor parameters determination. See you in the next chapter.